I'm the current job title, I think, is Chief Network Architect at Janet, which probably puts me in the same title as Neil. Oh, well, he's got a new title. There we go. So, first of all, a quick kind of brief rundown on what Janet is, for those who don't know. It's basically the UK's research and education network. Every country's got an NREN. Janet is the UK's one. We connect the higher education, so that's universities, the further education, the schools, and via a bunch of aggregation networks we connect, further education colleges, and via a bunch of aggregation networks we connect the schools. In addition, we connect a lot of the research institutions, so places like Jodrell Bank, the Diamond Light Source, the big sciencey sort of things. And where do we connect them to? Well, we connect them to the internet, of course. We do that via transit and peering, the same way you all connect up your ISPs. Then we use a network called Géant, which is a kind of NREN network of networks across Europe to connect to the other research and education networks worldwide. Since when? I'm glad you asked that. It's since 30 years ago this year. Janet started in 1984. Donations of cake are always welcome. On the backbone, that means we've been around for a while. We've seen X25. I mean, we started off thinking, who needs this IP lark anyway? Then we moved to IP over X25 because we realized there's this thing called the internet starting up. Then we used SNDS, which according to all our network diagrams appears to be one of the first cloud services. Moved to ATM, which was really just very dull with circuits. Then we moved to a POS network. No, packet was fine. 2.5 gig, 10 gig, 40 gig POS. We liked POS. It gives us lots of error counters, lots of alarms. It helps us figure out where things are going wrong. And lately, 100 gig E, for about 2 years now. So SuperJanet 5, the previous incarnation of the network, started operation in 2006. And like most of the previous ones, the transmission layer was not managed by us. It was dedicated to us. There was dark fiber, there was Sienna equipment on top of it, but that was managed by Verizon Business, and we managed the IP routers that lay on top of that. It was another POS network. Started off 10 gig POS. We moved to 40 gig POS. See the presentation I gave at UKNOF27. In case you can't remember that, I'll be asking questions on Polmux QPSK later. Polmux QPSK gives you 2 bits per second per hertz on the optical spectrum. So Neil was talking earlier on about their new fastest transmission, which is 5.7 bits per second per hertz. Sorry, 5.6 bits per second per hertz, wasn't it? And then 100 gig E, which gave a talk on a couple of years ago now. We've been running 100 gig E for 2 years. And at the presentation I gave 2 years ago, I was saying I was building capacity to last until 2013. It's now 2014, and all good things must come to an end, especially RNE networks built under fixed-term contracts with cyclic funding periods. So, the prologue. Before we built a network, we wanted to ask what our users wanted. Now, none of these answers are going to be particularly surprising. Everyone wants reliability. Lots of universities now outsource a lot of applications to either Google Apps or to the Microsoft Live Edu or Live 365 or Office 365 or whatever it's called. There's lots of remote teaching that goes on. When networks stop, the business of the university stops. RNE networks have not been experimental networks for a long time. Now, lots of our researchers want them to be experimental networks, and that's one of the interesting challenges of working on an RNE network, is balancing the experimental demands with the day-to-day 5.9 style production environment. Scalability. Imagine a graph that goes up and to the right here. I can't be bothered to paste one in. There's a bunch of big science projects as well. There's the Large Hadron Collider. That's currently shut down for 2014. It will restart later this year, early next year, with far higher data rates because they're increasing the energy of the collisions. There's ITER, which is fusion reactor research. that's based on a fusion reactor they're building in the south of France, but is being designed using compute resources in Japan, Rokkosho in Japan, and there's a lot of data being crunched by British scientists as part of that. There's a square kilometre array. Again, the headquarters for square kilometre arrays in Manchester, but the arrays themselves are being built in Australia and New Zealand and South Africa. Australia, a couple in New Zealand and South Africa. And it's scalability in terms of cost. Power, space, engineering resource, simple money. And it's flexibility. I mean, you know, who knows what things are going to be like in a few years' time, what the requirements will be. We need to be able to meet whatever the researchers, the universities ask for. Then there's separacy. Now, I have a strong personal opinion, which is don't trust the network. If you want security, do it at the endpoints. The network should just be a dumb thing that shifts packets. But that's not the way everyone sees things. There's the public service network, designed by industry in collaboration with the Cabinet Office, which is qualified to various impact levels based around confidentiality, integrity, and availability metrics. So each of those rates, I think, is 0 to 6 or something like that. So a highly available network, but doesn't meet much in the way of confidentiality or integrity is 004, which is basically what we classify Janet as. Impact level 2, I think, it goes to 224. So you have certain levels of separacy for to enable confidentiality. And we've got a lot of public sector customers, so we need to be able to interoperate with that. So what do we want? We wanted dark fibre. That's because all cool kids are doing it, and we couldn't seem to be left behind. But really, no, I mean, we do have some novel requests coming into the research environment. We want to be able to scale things up. One of the groups working at the NPL, the National Physical Laboratory, want to do stable time distribution using pure single fixed length wavelengths, a very pure reference source that they'll pass in both directions down a single bit of fibre to measure the interaction between them to cope with distortions, and that's then going to be used to distribute time between atomic clocks around Europe. So the MPL will be talking to the French and German ones and the Czech ones, trying to make sure that they work together to get a very, very stable time reference. And also, to meet the scalability, you want to control of the transmission equipment. Having somebody else manage it meant that there was a layer of overhead. Whenever we wanted to do something different, build more capacity, we had to build up the case internally, then go to Verizon Business, build up the case with them. We didn't have direct visibility of the optical kit, so anything that they wanted to do, anything we wanted to do, we weren't even sure whether we'd have enough space to do it, what it would entail. It was almost a black box. We want to do this, and say, well, it has this knock-on, that knock-on effect. So having control of it would mean that we removed the overhead. It means we had good knowledge of what's underneath. We can expand it, knowing what scope there is for expansion, and we understand when we want to do something new, what the implications are for the transmission equipment. Well, one of the other things we looked at is having a thin transmission layer. At the moment, most traditional networks are based on routers with grey optics, talking to grey optics and transmission equipment, which then carries the signal to some other router, where it goes to some other transmission equipment, where it goes to some more grey optics, which then goes to another grey optics and more router. If we could just have a thin transmission layer with DWDM optics straight in the router, then you'd avoid paying this penalty of going between optical and electronic and optical again at each side. It's getting there for 10 gig. For long haul 100 gig, it's still nowhere near there. It is still quite a long way away. So we weren't going to be able to do that. It's something we're tracking, something we'd like to be thinking of doing in the future. Of course, when you speak to optical vendors, they say there's no point in doing this. When you speak to, you should have a really thick optical layer and a really thin routed layer to do all of our OT and switching. You speak to router guys, and they say, oh, yeah, you just need a thin optical layer. What you want is a great big router on top. Now, how we bought it. don't worry, I'm not going to go too much into the European procurement process. It was a competitive dialogue process. 2 procurements, one for dark fibre, one for transmission equipment. There's several acronyms there. I don't know whether you want me to expand. The PQQ is a pre-qualification questionnaire where we send around something that says, are you fit to supply this sort of equipment? You know, people reply and we kind of say, okay, you look dodgy, you don't. Unfortunately, they mainly look dodgy. Then there's the dialogue process where for each of the procurements, we ended up with a good half dozen bidders that got through the PQQ. And for each round of dialogue, we had half a day's meeting with each of them. And there were about 3 rounds of dialogue. So that's a lot of work just in terms of preparing the requirements at each round. There's half a day of dialogue per bidder, feeding that back into the requirements, and then doing the whole cycle again. I mean, it was 2 weeks at a go just for the meetings with the bidders for the two procurements, and then repeat that a couple of weeks later. But enough from that. What do we get? You're not meant to really understand that map. It's kind of deliberately vague. About 6,000 kilometres of dark fibre, but only about 24 k's of that was new dig, which is good because we wanted to get this in in time. Just don't ask me how close we came to cutting through one of Glasgow's main HV cables during that 24 kilometres. We've ended up with, because we've gone with SSE Telecom as the provider, we've got a lot more aerial fibre than we have than we had in SJ5, and a lot less rail-side fibre. It's going to be interesting to see how that pans out. At our annual conference next year, I know that one of the ops directors is already getting used to the difference between L-type and T-type and all that sort of pylon with tracking a failure that happens over Christmas. This morning we were talking about different fibre types. Almost all of the Janet fibre is G652. Chromatic dispersion is not much of a problem with coherent detection. So it's G652, G655. It doesn't make much of a difference. What you really want to do is avoid transitions between the two on the same span. And G652 is, with most of the 65 Sienna equipment, which I'll come on to in a second, slightly better. So the transmission kit. It's the Sienna 6500 stuff. It's coherent optical, so we can go from one end to the other, one end of the country to the other at 100 gig E without regeneration on fibre that's 15 years old or more. I think we tried to get all fibre that's made after 2000. Even so, not all of the fibre some of the fibre is older than that, and it all works with this. You don't need brand new fibre. The traditional optical networks have a lot of dispersion compensation. We have no dispersion compensation in Janet because of the coherent optical doesn't require it. But one of the problems with that is that you can't really do the traditional on-off keyed signals for any reasonable distance, which means that the minimum wavelength capacity we have is 40 gig a second. If we build up a 10 gig circuit, then the chances are we're going to be wanting more capacity, so we build up 40 gig and put a 4x10 exponder on it. So the circuits we can carry at the moment are 4x10 or 40 gig E or 10x10 or 100 gig E on 40 and 100 gig carriers. It's possible to do 10 gig 10 gig wavelengths, but it's really not worth it. And with a kit, you can do up to 88 wavelengths, but we probably want a VAC space first because 88 wavelengths requires an awful lot of transponders. High level of the IP map, again, it's not supposed to be that clear. It's been had by our marketing guys with all pretty colours and coffee stains over it. We've got 2800 gig E circuits across the network, 2 by 100 gig E on some of the hot routes, and 160 10 gig E, mainly the regional access. Router-wise, we had T1600s before. We've gone for T4000s because it was an upgrade path. The T4000, you get 2 by 100 gig E or 24 10 gig E's per slot. And the cost is about a third of that of the T1600 for deploying a single for 100 gig E. And it also gets around the pretty horrible hack that the T1600 had, where it only had 50 gig forwarding engines, so you had to split the traffic between the two forwarding engines using either VLAN steering onto the PFEs or multicast bit hack if you were talking Juniper to Juniper. I mean, already some of these T4000s have got 700 gig interfaces in it, and that's one of the interesting bits is how we scale routing. I'll come on to that in the kind of closing slides. The next question: 100 gig optics. 100 gigabase SR10 or 100 gigabase LR, sorry, hanging shift key there, LR4. Already we're just kind of going between neighboring racks and transmission equipment and routers in neighboring racks. LR4 has lots of benefits. It uses normal single mode fiber patch cords. Great. We know how to clean those. We've got plenty of them in stock. It fits in with existing ODFs. You just do a patch from there, patch to there. You've got your single mode fiber between your racks. SR10 uses 24 multi-mode cables with MPO connectors. You need special tests kit. You need special cleaning kit. It doesn't fit with existing ODFs. The cabling is expensive, but it's much, much less expensive than LR4. Now we've got 28 100 gig circuits, so bear in mind that's 56 optics across the network, 2 in the routers, 2 in the transmission kit for each circuit. And going for SR10 rather than LR4 saved us about £1 million across the network. So you can do the sums to figure out exactly how much it's saving per optic. So SR10 it is then. Fibre to our good friends in Ireland. So we have part of Janet is in Northern Ireland. Then we also peer and work closely with our friends in HANet. And we also provide some of the connectivity between Giant and which is the European network of networks, of RNA networks. Now, we have fibre from Lytham St Anne's to Dublin and from Renfrew near Glasgow to Belfast. Most of the spans on our network are about 80 to 120 kilometres. You can maybe cope with about 24, 28 dB before you start having to do some sort of powerful amps. These are 238 kilometres with a 48 dB loss and 203 kilometres with a 44 dB loss. So this is where we have to bring in the big boys, the submarine Raman amplifiers. The armoured cable you can see off the top of the kit there is so you don't unplug the fibre. We are told never, never, ever unplug this fibre. It's taking so long to get it working. You have to tune it, you have to polish it, you have to polish it again. Rubbing it on your jeans just doesn't work these days. To get it working, there's the Sienna guys, there's a lot of optical simulation. There's precise setting of the amplifier bias cones to be sure that it is going to work. They put it into service, it dropped out. A bit more tuning, a bit more simulation, it still dropped out. A bit more simulation, I said, okay, let's just turn all the bias cones up to maximum, and it works. There we go. So a few more submarine fibres we've got on the submarine fibres. Because of that, it does actually reduce the channel count slightly, but we're not going to be needing 8.8 terabits to Ireland in the immediate future. Maybe technology will advance by the time we do. We also have some submarine fibre between Aberdeen and Dundee. It's across land, but it's a very long stretch. So we've got submarine amps that go in a couple of university premises next to each other in Aberdeen and Dundee. The acceptance testing was a fun bit of my time last year. 6,000 kilometres of duplex fibre, so that's 12,000 kilometres of fibre. Splices at least every 2 kilometres. OTDR reports from each direction on the fibre, and having to browse through each of those manually. Chromatic dispersion reports, polarization mode dispersion reports. At the same time, I was in the US for a meeting. The optical specialist was in India with his family, and the project manager in the UK. So we had about a couple of hours a day where we all get together and talk. Otherwise, we were kind of just locked in different rooms, poring over reports. About 80 reports, about 80 POPs, each of which we had VAC layers to do, cabling and acceptance reports, quality assurance reports. The acceptance testing took actually a long time to be sure that what we got was right. So, I mean, we're working to a fixed schedule. The SJ5 contract finished on the 23rd of October 2013, and there was no chance for extension. We had to complete the build and migrate by that day. One of the project managers calculated that we had about 512 hours worth of meetings. Sometimes I think that was per week. One of the other ones calculated that we'd counted about 19,000 emails sent to the project. On the 4th of March 2013, there was a bit of a logistical clash where we had our own engineers, we had Sienna engineers, we had Sienna's installation subcontractor, we had router installation guys, we had DC power installation guys, and we have Fibre engineers all in the same pop on the same day. That's 22 engineers trying to work around about 4 racks. And sandbags. One of the pops we got, we turned up, the people had routers, and there were sandbags outside. I was like, oh, yeah, don't worry about that. It's only in case it floods. Some more challenges. We prefer pre-built racks rather than kind of bringing in flat pack and assembling themselves for stability. Now, not all the pops are as easy to access as any other. So that's installing one of the racks in a certain pop in the northwest Scotland. Put it in and over. I was a bit disturbed to see them. Didn't appear to have any sort of paper or towel over the handrail, sort of getting scratched, but you know. This is not an actual photo of what happened, but one of the fibres to Ireland, we got a maintenance report. The Royal Navy will be carrying out a controlled explosion of a mine that's been found near your cable. Service is at risk. So a bit on the operational support. I mean, so we've been an IP shop until now. We've only managed limited amounts of DWDM, so we've been able to cope with having a few different windows open. We've had an HP Open View window open, actually we still use snips as a backup for that, and we had Sienna on center for the old Sienna kit we had. As we're managing a national network, we need to kind of scale up that. So we're in the process of writing a bunch of modules that will speak to the IP network. Quite simple, but then use TMF814 to speak to the optical kit as well and present a kind of unified view of the alarms. This is a work in progress. I might see if I can get one of the guys to talk about it at a future UKNOF if it's interesting. And a couple of observations. Dark fibre. Buying dark fibre was not easy. Nobody wants to sell it. BT claim they can't sell it. Most prefer to sell services. And I don't know what it's going to be like in 10 to 15 years when we need to renew the contract. We ended up with 2 realistic competitive bids at the end of the process out of the 6 providers that started. What's in the name? It's been mentioned already. This is not a talk about deploying IPv6. Janet6 does not have anything to do with IPv6. We've been doing it for 15 years of our tunnels, a decade dual stack. But we had some of our users say, oh, I'm not interested in Janet6. I don't believe that v6 thing is important. No, this is your new network. You will be getting Janet6. Power and cooling are still an issue for us in some data center operators, especially the telco-focused colo ones. Telco-focused colo. The T4000 requires 12 60-amp 48-volt DC feeds, 6 actives, 6A, 6B. Each 6500 shelf requires an A and a B 60-amp feed, and some POPs have 5 or 6 shelves. So it requires quite a bit of dialogue with the colo providers to say, right, well, that's the theoretical maximum. What we're actually drawing is significantly less than that. And as I'm sure you're aware, buying a little bit of empty space. Figured out we've got 155,000 square foot of colo space just for transmission and routing kits across the UK. I've been told to finish. It's my last slide, I think. So where we go next, we're expanding the fibre footprint. There's some e-infrastructure funding we're using to build out to places like the Met Office, which does a lot of, obviously does a lot of climate research. They do a lot of data transfers. The European Bioinformatics Institute in Hingston, the Francis Crick Institute, which is that big building site next to King's Cross Station, into our regions. Working on the stuff that Neil just talked about. In fact, Neil mentioned after lunch, increasing the density of the transmission equipment. Adding new chassis is expensive. We'd far rather kind of build up density. So moving from QPSK to QAM, FlexGrid, changing from MEMS WSSs, which kind of basically little mirrors that kind of go back and forth, to liquid crystal ones. Increasing the density of routers. Again, see what I'm saying about adding new chassis. We'd rather fit more into one chassis than install more chassis. And as most ISPs might be looking at, changing how we distribute traffic, rather than pulling it into a couple of core nodes and shifting it from there. More regional peering, more local content delivery, more optical bypassing, but then you need more interfaces at the hotspots, even if you need fewer ones at the intermediate POPs. And that's it. Questions, or I don't know whether we have any time for any. But, oh, a question from Neil. Is that his first?
I'm kind of interested in two things. Why I'm amazed you picked T4000 per port cost is mind-blowingly expensive, and you can quote me on that. And two, degrees of ROADM in 6500. What did you go for that? I didn't see it.
Yeah, we picked the T4000 because there was a capital injection. We had existing T6000 chassis. Upgrading the chassis itself was a fairly minor cost, but I mean, the chassis is not the major cost anyway. It is the interfaces. At the time, we got a reasonable deal that didn't differentiate it that much from, say, the MX series. I think when the T series lifetime is up, that's something we'll look at. But for now, it wasn't a bad economic choice.
And did you go out to a full tender with other vendors, though, or?
For this, no, because it was an upgrade. Right. We had quite a lot of in-depth dialogue with the bidders, and that was almost a threat that we could use. It would give us a really good deal. Make sure we're spending this money wisely. On the degrees of ROADM, it varies depending on which point of the network are. Some of them are 5 or 6 degrees. Because we have fibre coming in from regions, as well as maybe 3 or 4 directions of core fibre going through there as well. But it varies. It can be 1, 2, 3, or 5. And well.
Oh, sorry.
Donald Cunningham from Airspeed. The DC power requirements were quite interesting. Did you have any pushback from the data centers on providing that amount of DC power?
Yes. We had a lot of pushback from that. I mean,
did it involve swearing?
Hell yes. No, it's depending on the data center operator you're talking to. I mean, the ones that are more focused on co-location of servers are more used to, of course, the AC delivery. So at that point, we have to put in our own rectifiers. The ones that are more focused on telco equipment are more geared up to providing DC straight to the rack. So there were kind of 2 different branches, but they're usually then focused on smaller power density. So it's a matter of either different approaches with each vendor, or with each supplier, as that region required, or as that site required.
One thing to note is just one thing that I ran across in a previous life, which is where is having separate breakers for your feeds, for your DC feeds, because sometimes what happens is somebody will say, oh, I'll just put in a 3-phase breaker here, and one phase going walkabout will in fact take down your entire DC to a rack.
Yeah. I mean, we've got quite a bit of monitoring on the power supplies, and we have, obviously we've tried to go through the whole thing about A and B feeds, make sure they're fully diverse within the data center and different external feeds. But there's only so much that you can do, and sometimes things will happen behind your back, and one day you wake up and something's gone dark.
Did you, or was thought ever given to battery backing the rectifiers at any point, or did some of the data center providers say, hell will freeze over before we let you UPS feed a large draw of batteries? Thanks all the same.
We didn't really. We thought we'd go for. We specified in the tender the amount of UPS and generator backup that the co-location provider should have. So we went that route rather than put it in our racks.
Thank you very much.
Okay. Right. We'll have to stop taking questions now because we're getting quite a bit behind.
Oh, so, sorry. I'm sitting next to him. You can ask me in a minute.